I wanted to take a few minutes to discuss carbocation rearrangements. And as we've said before, and as you've read in the book, whenever you have a secondary cation, it's a good idea to ask yourself if we can possibly have a rearrangement and thus go to a tertiary cation. And of course, we're never going to see a primary cation, and if we start with a tertiary cation, chances are we don't need to rearrange it. So here I have a number of secondary cations that we'll discuss. So the first thing to do is to evaluate the two sides of the cation. If there's a secondary cation, there are two carbons that are next to it, of course. That's the definition of secondary cation. If you can visualize the hydrogens, that's great. If you need to draw them in to help you discuss this, that is fine as well. So now we're going to look at possibly rearranging, moving one of these atoms or groups in the hope of generating a tertiary cation. And in this molecule, there is only one possible way to generate that tertiary cation. I hope you can see that if we take either of these two hydrogens on the right, we're going to result in just another secondary cation. If we do this, right, we get a molecule that has a cation here, and everything else is basically the same. So all we've done is move our secondary cation around. So that's not going to work. So let's not do that. And of course the other hydrogen will give us the same result. So that's not going to work either. But you see that the left hydrogen is attached to, now it's attached to a carbon that's a tertiary carbon. It has 3 carbon groups to it. So that gives you a good clue that if we do a hydride shift like this, we should be able to generate a tertiary cation at that tertiary site. So this is good. This is what we want. And so that's what we have to evaluate. We generally have to evaluate both carbons that are attached, and it will become very quickly obvious to you with practice that any carbon that looks like that next to a secondary cation will not help us and does not need to be considered further for rearrangement. Let's look at the second molecule I have here. We have a secondary carbon here, and on the right side we have a primary methyl, essentially. But if I were to remove one of these hydrogens, I'd generate a primary cation, so that's not going to work. And on the left side, I have a CH2. At first glance, it looks like it wouldn't give us a very productive rearrangement either, but let's just draw the product and see what we get. So my cation has seemingly moved over, but really we've filled in one empty orbital and left behind another empty orbital. And now can you see any unique features of this same secondary cation? Hopefully you've recognized that this is a allylic cation, and we can draw a resonance structure. Which puts a primary cation on the left side, but since it's a resonance structure, that's reasonable and allowed. And now we have a cation that's in resonance. And of course, as we've learned, being able to have resonance makes a much more stable ion or molecule. So this new secondary cation is much more stable than the original secondary cation because of the resonance possibilities. So here we have an example where we might rearrange just to allow the molecule to have resonance possibilities, even though we're not forming a tertiary cation. We're forming a secondary cation, or more properly, an allylic cation, which we know can participate in resonance. And thirdly, we have this secondary cation down here. To the right, we have another secondary carbon. We know that that's not going to give us any sort of fruitful rearrangement unless there's a double bond nearby, and we don't see any double bonds. Over here, we have what we call a quaternary carbon. I'll abbreviate it, but quaternary meaning 4 carbon bonds to the carbon, or 4 bonds that are not hydrogen to this carbon here. So that could allow perhaps the production of a tertiary cation if we take one of those bonds and migrate the entire alkyl group here. So here we have a methyl shift. And so that will result in something that looks like this. So I've left behind an empty orbital by moving the methyl and its electrons, and I've put the new methyl, so this is the same methyl that we moved, put the new methyl where the cation used to be. And so now I have a tertiary cation, so I have a more stable molecule, or ion in this case. And of course, I think you'll agree that if we have 3 different alkyl groups here, I'm going to add some more carbons now. Now I have a methyl, ethyl, and isopropyl. Any one of those could migrate, and that would give us 2 other possibilities. And I'll leave that up to you, but certainly you could envision using that blue arrow in a alkyl shift instead of the green arrow, or this second blue arrow in an alkyl shift instead of the green arrow. So if our quaternary carbon has several different groups on it, that can lead to a bunch of different products. And as we'll see in the future in this class, that's really an undesirable outcome. So we try to avoid that, and thus we try to avoid forming this secondary cation because it would rearrange into a number of different products, and maybe this one here is the only one we want. So we have 1/3 of our products as our desired product and 2/3 of them as something we don't want, and that's going to take a lot of time and effort and potentially money to get rid of these 2 undesired products that we don't want to form. So oftentimes we try to avoid rearrangements because they can lead to a lot of different products. But sometimes, as you saw maybe in our first example, there's only one outcome, and it leads to this tertiary cation here. That would be fine because it gives us only one product.